Okay, this is section 2.7. We're going to do three things. We're going to look at residual plots and understand what those are. And they're going to tell us whether a linear regression model can be used or if it's nonlinear. So in SOFA, the form. We're going to interpret the standard deviation of the residuals. We're going to use the letter S for that. And we're going to interpret what R squared is. It's called the something of determination, coefficient of determination. Okay, it's called the coefficient of determination. We just use R squared for that. Okay, so first thing is a residual plot. So basically, the other day we've talked about what residuals are. Okay, residuals are the amount of error we have, right? So remember, the residual was our actual minus what we predict, right? Okay, and if we have a point above, okay, that's that distance right there, how much error there is the residual. That has a positive residual. And if we have a point below, that distance there would be a negative residual. Okay, so a little review there. So if we look at this, we're going to take each individual point. Okay, this point right here would be, I don't know, about 600 or so or 700 off of, right, off of the predicted. Okay, so, and it's positive, it's above. That's this point right here. So here is the 0. That's basically our line here. And for this point, which is a little bit above 0, so the x-axis stays the same, but our y-axis is the residual amount. So this residual would be, I don't know, 600, 700. So right here is that residual, 600 or 700. Okay, if we pick a different point, this point right here, at 5, that residual looks like it, I don't know, a couple hundred. So at 5, that residual is a couple hundred. Okay, this, say at 20, this residual is negative something. So at 20, this residual is negative something. Okay, so we're just looking at all those residuals. Basically, you can see the form of this. Remember in SOFA, the form is either linear or we're going to say nonlinear, right? Okay, so we're thinking about one of those two things. So if we're looking at this right here, you can see from this graph, I don't know whether linear is really good or not very good. Okay, so, but this you can definitely tell. So by looking at the residual plot, you can see that form to it, and we can see that it's not linear. Okay, for it to be linear, you would be looking for a good scattering of points all across. You wouldn't really see a pattern to it. Then we could say it's linear, and the linear regression model, you know, y equals mx plus b would be a good fit then. Okay. So here's another one. This was the price of the Ford F-150, miles driven, and the price. Okay. So here, if you see this, okay, there's our line. This residual is a negative. You can see right here that residual is a negative. Okay, you can see all these different points here and all the different points here. Basically, if it's below the line, it's a negative residual. Above the line makes it a positive residual. Okay, now this one, you see a good scattering of points. You don't see a form of it, like a nonlinear form like you did in the previous example. This would be a good linear line, okay, because we see a good residual there. Plot. Does that make sense? Okay, so I might give you different residual plots and say it'll give you, tell you is linear or nonlinear. Okay, so that's one way to tell linear versus nonlinear. Okay. Next problem is this S. Okay, it's the standard deviation of our residuals. So if you remember what standard deviation is, right? A standard deviation, remember if we had a bunch of points, okay? A standard deviation is basically, on average, how spread out something is. It's kind of the spread, right? So if we have our mean, we have the standard deviation, okay? And on average, how spread out is it, okay? So if we think about that here, we're basically taking all of our residuals, and we're going to find the standard deviation of them, okay? I'm not going to make you do it by hand, but I want you to understand what S is so you can interpret it. Okay, so if we take all these different F-150s, right? So we take all their residuals. This is going to have a very small residual. That's going to have a larger residual. This is positive, negative, right? All these residuals, okay? So this is an example of all those residuals right there. And if you find the standard deviation of these, and you can use Desmos for that, right? Remember how we found the standard deviation in Desmos if we have residuals? It comes up with a standard deviation of this. Okay, now we have to think about what this means. We said a residual was when I make this prediction for this vehicle, I am off. I made an error by about this much, right? And same with this one. Okay, this one's almost exactly on, not quite, but I made a little bit of an error. Here, I made a little bit of error when I predicted, right? Here it was some error. Here is some error. So residuals are basically just the error that we have when we made our prediction. Okay, how far off were we when we made our prediction? Okay, so this is basically saying our S value is basically kind of our average error. So when we're making a prediction based upon miles driven, we're going to be off kind of an average of $5,740 when we make a prediction. Okay, so based upon a certain many miles driven, when I make a prediction, on average I may be off either above or below an average of about $5,740. Okay, so that is the interpretation of the S. Okay, based on the actual price is typically about that much away from the predicted price. Okay. Okay. The third term is the R squared, the coefficient of determination. Okay. I will tell you there is a direct relationship. Remember our correlation, right? If we have R is 0.8, we say it's moderately strong and positive, right? We can just take that and square it. So our R squared is 0.64. So there is that relationship there. That's not exactly how it's calculated, though. And it's actually a very complicated process as to how this is calculated, which we're not going to get into. But I want you to be able to interpret what this R squared means when we give you this number. Okay? Basically, it says this. So I'm going to show you how it's calculated, but you won't have to. This basically just helps you to understand the interpretation. Okay? So if I take, okay, so the price of the vehicle and the miles driven, right? Okay, we had this correlation. If I just take all these trucks that were sold and I find the average price. So the average price, so if I add them all up and divide by how many there are, the average price would be about this much. Okay? This would be the least squared regression line with that line. Okay? So we would have a sum of the squares would be this. How much better is it if I'm using the least squared regression line versus just the average line? Okay? So the least squared regression line is this. To find R squared, they subtract those two and divide by the least squares regression line with the average. Okay? You don't need to know too much about that, but this is your R squared here. Okay? So if you get an R squared of 0.66, that means this. In class, I asked you, what determines the price of a vehicle when it's sold, right? And you said miles driven. Okay, that makes a big difference in the cost. Some people also said whether it has been in an accident or not. If it's been in an accident, then the price would be less. If the paint's been all scratched up, it'd be less. If it's been kept in really good condition, it might be more. If it's a certain color, sometimes that's more than a different color. So there's a lot of other factors other than just miles driven that determine the price of a vehicle. Okay? So what we're saying here in this problem is that 66% of the price can be predicted by how many miles there are. Okay, think about that again. 66% of the price can be predicted based upon how many miles are on the vehicle. Now, there's another 34% that we don't know about, right? So the other 34% is can be predicted of the prediction price is other than miles driven, like the paint job or how old it is, or those other factors. Okay, so 66% can be explained of the price can be explained by the miles, 34% with other factors that we're not sure about in this problem. Okay, so if we look at this, there was a problem with how many times you tap on the top of a bottle can, and if it explodes or not. Okay, so how many seconds you tap on the can versus how much soda is remaining in the can afterwards. Okay, so we have less soda remaining in the can, which means they're shaking this. Okay, they're taking this can, they're shaking this can up, and if they don't tap on it, a lot of it comes out and there's less soda left, right? They said if they tap on it for 12 seconds, whether it's actually the tapping or the actual time, I don't know, but anyway, so they tapped on it for 12 seconds and not as much spilled out, right? They have more soda in their can. Okay, so they gave an R value for 0.85. Okay, R squared value of 0.85. That means that 85% of the variability of the amount of soda remains is accounted for by the least squared regression line, which is tapping. So tapping accounted for 85% of the variation in here. Okay, now the other 15% would be other factors. It might be what type of soda, or I don't know, other factors that are determined, how it's bottled, different things that can be accounted for with that. So I want you to memorize this equation, this sentence. Okay, this is how you're going to interpret it. We're going to say whatever percent of the variability in whatever your y variable is accounted for by the least squares regression line with whatever our x variable is. Okay, so if I ask you to interpret it, you could use that sentence. Okay, you could also explain the amount of soda remaining. 85% of it can be explained by the tapping. There's another 15% of it that is not the tapping, some other factor. Okay, so let's look at one more problem here. Okay, can you predict the battery life of a tablet using the price? Okay, so if a tablet is less expensive versus more expensive, what will happen to the battery life of it? Okay, so this is the residual plot for it. Okay, this is our line of best fit. That's saying that our line of best fit for price and hours the battery lasts would have a starting point of 4.67, and it has an increase of that much. Okay, so we have our line of best fit. So it says it has a positive slope. The more a tablet costs, the longer the battery life is going to be. Okay, but anyway, let's look at the residual plot. Now, by looking at this residual plot, is it appropriate to say that it's a linear model? So if you're thinking about sofa, is it okay to say that it is linear? Okay, I would say yes. We have a good scattering across here, which is what we're looking for. There's no pattern that we see within it. Okay, next one, S. If S equals 1.21, okay, what does that mean about price and number of hours? Okay, so think about that's the residuals of our, right? That's the average error. So we can say when predicting how many hours a battery lasts, we are off, or we're inaccurate, an average of 1.21 hours. Okay? It's our average error. Okay? So our average error when making a prediction, we're off by 1.21 hours. Okay? So next one, r squared is equal to 0.342. Okay, so if you remember that sentence there, we would say 34%, 34.2% if you really wanted to, okay, of the variability in my y value. My y value was the hours, is accounted for by X, our price. Okay, so only 34% is the price. So if we're trying to predict for how many hours based upon the cost is only going to account for 34% of the variation in that, which means there's other factors out there that has a lot of other factors. So 66% of other would have other variables rather than cost. So cost is probably not a great predictor for the number of hours it'll be. Okay, so that is section 2.7.